Hello students, welcome to our channel physics class, and today we'll be doing some numerical problems on magnetism due to moving charges. So let us go to the first problem. So in this problem we are given with two identical magnetic dipoles. First dipole we are calling as A, which is a permanent magnet, and the second dipole, which is magnetic dipole, we are calling it as B. So these are the two permanent magnetic dipoles, and these are kept at a distance of small d. And it is given that the magnetic moment of each of these permanent magnets is m. So capital M is the magnetic moment of each dipole, each permanent magnetic dipole. And as you can see in the figure, the axes of these two magnets are perpendicular to each other. So we have to find out the magnetic field at any point P, which is given in the middle of these two permanent magnets. So we have to calculate the magnetic field at point B. So that is the question we have to solve. So let us go to the solution. So first of all, we have to write down the magnetic field due to permanent magnetic dipole A at any point P. So just use the formula that P due to A at any point P is mu naught upon 4 pi. And we have to write it in terms of the magnetic moment. So it will be 2m. And because m is equal to I into A, so simple use the formula for this magnetic field. So this is twice of the magnetic moment and 4 pi, and here we have to write down the distance of this permanent magnetic dipole A to the point P. Since this total distance is d, so from this permanent dipole to point P it will be d by 2. So we can simply write it down as d by 2 whole cube. So the formula we have used here is B is equal to mu naught upon 4 pi 2m upon r cube. This formula we can easily get from the Biot-Savart's law in terms of the magnetic moment. Since in the question magnetic moment for each of the magnetic dipole is given to us as capital M, so we'll utilize the formula, and in this case R is the distance from this magnetic dipole to the point P where we have to calculate the magnetic field. So this we have taken as d by 2. Similarly, we can write down the magnetic field which is present by the permanent magnetic dipole B. So the magnetic field which they produced will be equal to mu naught upon 4 pi m upon d by 2. Again the distance is d by 2 from here to here. If you take the distance, it's just a half of small d. So this we are writing as d by 2 whole cube. Then why there is a difference in between these two magnetic fields due to A and B? The reason is that point P is on an AND position. As you can see that this point P is on AND position for the dipole A. This is a magnetic dipole. So for this magnetic dipole A, P is at the AND position, and for the dipole B, as you can see, it is in the broadside on position. So we have taken as m, and here we have taken as 2m. And if you want to calculate the resultant field, the resultant magnetic field, that will be written as under root of BA square and B square. That is the magnetic field due to magnetic dipole A plus magnetic field due to magnetic dipole B. So if you put the value, we'll get it as, what we can take as common is mu naught upon 4 pi and capital M and d by 2 whole cube, that we can take as outside, and remaining here will be, here it is 1 square plus 2 square, because these are the common terms. So square and under root cancels out, so we have taken as common, and in under root here you will have 1 and here you will have 2. So this is 1 square plus 2 square. This gives us the resultant magnetic field. So if you calculate this, you will get the resultant magnetic field as, so this will be 4 plus 1 is 5. And here you have 4 and this will be 8. So this cancels out and you will have 2 here. So this will become 2 under root of 5 mu naught m upon pi d cube. So this is the resultant magnetic field we get due to the presence of these two magnetic dipoles A and B. And if you want to calculate the angle then you can get the value of tan theta. So tan theta will be equal to magnetic field due to B upon magnetic field due to A. So this ratio will again be, it is by 2 here, it is 2 here, it is 1 here. So the ratio will be 1 by 2. So our angle will be tan inverse 1 by 2. So now we know the direction. And we can say that if theta is the angle that the magnetic field due to A is making, then tan theta is equal to 1 by 2 or theta is equal to tan inverse half. So that is the answer. And this numerical is now solved. And if you want to show the direction here, then the magnetic field due to A will be in this direction. And the magnetic field due to B will be somewhere here. So this is how you can represent. And then we have calculated the magnitude and we have calculated the direction. So this numerical is now done. So let us quickly move to the second one. So in the next question, we are given with a bar magnet. It is having the magnetic moment capital M, and the value of capital M is given to us as 1 into 10 to the power minus 4 joule per Tesla. And it is free to rotate in a horizontal plane, and there is a horizontal magnetic field P, which is given as 4 into 10 to the power minus 6 Tesla. This is the magnetic moment is given, and this is the magnetic field this is given, and we are rotating this bar magnet in a horizontal plane, and we have to calculate the work done in rotating this magnet slowly from a direction parallel to the field of a direction at 60 degree. So parallel we can take as maybe 0 degree and theta 1, and theta 2 is given as 60 degrees. So we have rotate horizontally between these two angles, and these angles are from the field. So what is the work done that we have to calculate? Now let us quickly move to the solution. Whenever we have to calculate the work done, then it is always equal to the change in potential energy. So the work done is always equal to mb cos theta. This is the formula for the work done whenever we are moving a bar magnet in an external magnetic field. This is the formula for the work done, and here the work done is by the external energy, so we have to use a negative sign. So there is a negative sign, and always remember this negative sign is because the work done is by some external agency, right? So now we can calculate for different angles. We have to start from 0 degree and we have to add it 60 degrees. So now we can calculate the work done. That will be equal to the change in potential energy. So let us say we can get minus mb cos 60 degree minus of, because we have to take the difference, so this is minus mb cos 0 degree. So if we put the value of cos 60, so this is equal to minus mb cos 60 degrees, always 1 by 2, and this minus makes a plus, so this is plus, and cos 0 degrees always 1, so this is plus mb. So we have minus mb by 2 plus mb, so this is equal to mb 1 minus 1 by 2, so this is equal to half of mb. So that is the formula we get for the work done. And now since we have the formula, so the formula that comes out to be using the change in potential energy, the formula that is derived by us is the work done is equal to half mb. The value of m is given to us, the value of b is given to us. So simply substitute the value. The value of m is 1 into 10 to the power minus 4 joule per Tesla, and the value of b is given as 4 into 10 to the power minus 6 Tesla. So this will be equal to 2 into 10 to the power minus 10 joule. That is the answer. So this numerical is now done. And then you have to keep in mind that work done is equal to change in potential energy, and this formula in potential energy you have to remember, and rest everything is just you have to put the value in, solve the numericals. So let us move to the next one. So in this numerical, what we are given is that we are given with a rectangle. So there is a rectangle PQRS, and the center point is given as C, and one side is given as small a, and the other side is given as root 3a. And there is a current I which is flowing in this rectangular loop of side A and root 3a. The current is given as small I. Then we have to calculate the resultant magnetic field at point C, that is in the center of rectangular loop. Right? So there is a current, basically there is a current carrying loop which is a rectangular loop whose side is given to us as A and root 3a, and we have to calculate the resultant magnetic field at the center of this rectangular loop. So let us move to the solution. So if you look to the diagram, you can see that the magnetic field at point C due to all the wires will be directed into the plane of the paper, because if you fold your right hand fingers in the direction of flow of the current, that is in the clockwise direction, then your thumb will point downward. So that means due to the current flowing in the rectangular loop, the B is always downward. So the magnetic field is in downward direction into the plane of the paper. And to show the downward direction, we use the symbol cross. Right? So this is the direction of the magnetic field due to this current carrying rectangular loop. And also the magnetic field at point C due to PQ and SR is same, because these are the two same sides. PQ is similar to SR, so it is the magnetic field will be same. Similarly due to QR and PS, if you see, the magnetic field would be same. So we can calculate this to this side and we can double it. Similarly, we can calculate it to this side and we can double it. So we can write down the resultant magnetic field at point C. So the magnetic field at point C, that is the center of the rectangular loop, will be twice of magnetic field due to, say, PQ we can take. So we can double the PQ. So this will be due to PQ and SR. And plus we can get the magnetic field due to SP, that will be magnetic field due to SP plus magnetic field due to QR. So just double and we will have the resultant magnetic field. So just write down the formula. First of all, we'll calculate the magnetic field due to the side PQ and then we'll double it. So write down the formula using the Biot-Savart's law. So that is mu naught I is the current flowing and 4 pi. And the distance, if the side is A, then the distance will be A by 2. If you go to the center from this side, then this total distance is A, so this will be A by 2. So you can write on the distance as A by 2, 4 pi r. And if you go to the angle, if you go to this angle and this angle, then this will be, because this will be an equilateral triangle from here to here, so each angle will be 60 degree. So you can simply write it down as sine 60 degree minus sine 60 degree. So this is sine 60 degree plus sine 60 degrees. This is simply using the Biot-Savart's law. If you want to know about the Biot-Savart's law, you can quickly refer to our lecture on magnetism. The link is given below in the description box. You can quickly go through the theory. But for now, we have simply used the Biot-Savart's law and we can write on this formula. So the magnetic field due to PQ will be equal to mu naught I upon 4 pi A by 2 and sine 60 degrees root 3 by 2 and again root 3 by 2. So this is root 3. Or you can write it down because this 2 will go upward. So this is 2 root 3 mu naught I upon 4 pi A. Similarly, you can easily calculate the magnetic field due to side SP. Again, use the Biot-Savart's law. This is equal to mu naught I upon 4 pi. And this side is given to you as root 3a. So if you go from here to here, this is for SP you are doing. So this distance is root 3a. This whole distance is root 3a. So this distance will be root 3 upon 2 because this is just the half we have traveled from center to the side SP. So SP to center, we can say the distance is root 3a by 2. So R will be having the value root 3a by 2. Then you have to look at the angle, these two angles if you see. So this will be sine 30 degree plus sine 30 degree. Again using the Biot-Savart's law. So if we put the value, then this is equal to mu naught I upon 4 pi root 3a, and 2 will be here, and sine 30 degree is 1 by 2, so 1 by 2 plus 1 by 2, if you do, it will become 1. So the magnetic field due to side SP will be equal to mu naught I upon 2 pi a root 3. And now in order to calculate the total magnetic field, let's see, we have to just double these two quantities. This one and this one, we have to just double it. So simply put the value, the magnetic field at point C is equal to twice of this 2 root 3 mu naught I upon 4 pi a and plus mu naught I upon 2 pi a root 3. So this is 2 and 2, so this 4 cancels out. So this is equal to mu naught I upon pi a and with root 3, and similarly this 2 again cancels out, so this is mu naught I upon, so here there is root 3, so if I multiply and divide it with root 3, this will become 3, root 3 into root 3 will become 3, and here we'll have root 3. So I can again write on this equation as 3 mu naught I upon pi a root 3. Simply I have multiplied and divided with root 3, this first term, and this is I have written as such mu naught I upon pi a root 3. So this is mu naught I upon pi root 3, this is mu naught I upon pi a root 3, this is 3 plus 1 is 4. So we can join this and this will become 4 mu naught I upon pi a root 3. So that is the resultant magnetic field at point C at the center of the rectangular loop. So this numerical is now done. So the magnetic field at point C is 4 mu naught I upon pi a root 3. As simple to calculate using the Biot-Savart's law. So let us move to the next numerical. So in this numericals we are given with two parallel wires. These are two parallel long wires, and these are in the plane of paper, and they are carrying the coordinate 2i and I in the opposite direction. So the first wire is carrying the current 2i in the upward, and second is carrying I in the lower direction, and these are in the plane of the paper. And we consider a point A, which is at a distance small a from the first wire. Then we consider point B. Then we consider point D, which is at a distance small a from the second wire. And there is a point C. In between these two wires, and this distance is also A. So now we have to calculate the magnetic field at point A, C and D. So we have two current carrying wires carrying the current in opposite direction, and we have to calculate first at point A. This point A is a distance small a from the first wire. Then there is a point C which is in between these two wires carrying current 2I and I in the opposite direction. And the third point is D, which is at a distance small a from the second wire. So we have to calculate the magnetic field at these 3 points. So let us go to the solution. So whenever you are studying about these two parallel current carrying wires, then they produce a magnetic field and they affect each other. So first we have to calculate magnetic field at point A. So we'll do them very easily one by one. Let us move to the first point and let us say that we are calling this as magnetic field due to wire 1 is B1 and magnetic field due to wire 2 is B2. So again you have to use the right hand rule, and if you use the direction of current in the upward direction, then for the first wire the magnetic field will be going outward of the plane of the paper, and for the second wire it will be coming downward, it will be going into the plane of the paper. This you can simply do using the right hand rule. Now we have to calculate the magnitude. After knowing the direction, we have to calculate the magnitude. Again, we have to use the formula B dot dl is equal to mu naught I. We have to use Ampere circuital law. If you want to know about the details of the Ampere circuital law, you can refer to my lecture. The link is given below in the description box, where we have detailed description of how the current behaves, how the magnetic field is produced, and which formula we have to use. So using the Ampere circuital law, we can write down B1 into, that is a symmetry, it has a symmetry. So let us say that this distance is A, so we can take it as 2 pi A. The radius for point A you can take as A, because you can make a circuital loop of radius A around the first wire. Then this is equal to B dot dl is equal to mu naught I. And here the current is 2I, so the current is replaced, small I is replaced with 2I. So that shows that B1 will be equal to mu naught I upon 2 pi A. Very easily you can write down using the Ampere circuital law. And similarly, if you want to write down B2, again you have to use the Ampere circuital law, then B2 into, then if you calculate the distance of this point A from the second wire, then this is A plus A. So you have to make a circle of radius 2A. So this will be 2 pi and the radius will be 2A, right? Here the radius is A because the distance of the first wire to point A is A, but the distance of second wire to this point A is A plus A 2A. So the radius will be 2A. So if you make an Ampere circuit, then it will be a circular loop of radius. It is a wire, so it will have a cylindrical symmetry. But if you draw a circular loop, then the radius will be 2A. This is equal to mu naught and the current is I. So you can simply write down B2 will be equal to mu naught I upon 4 pi A. So that is the beauty of Ampere circuital law, that can make you write down all these fields very easily. So that we have done for point A. So if we calculate the resultant field at point A, then this will be equal to, this is mu naught 2I upon 2 pi A. So this 2 cancels out. So this is mu naught I upon pi A, and this is minus mu naught I upon 4 pi A. So if we take mu naught I upon pi A is common, this is 1 minus 1 by 4. And 1 minus 1 by 4 is 3 by 4. So this is 3 by 4 mu naught I upon pi A. So this is the resultant field at point A. So the resultant magnetic field at point A is 3 by 4 mu naught I upon pi A. We are easily calculated using the Ampere circuital law. Similarly, we can calculate it for point C and point D. So the magnetic field at point C. Again, simply use Ampere's circuital law. Then if you go to the point C, then if you see from the side of C, then for the wire 1, the magnetic field is downward because the direction is now reversed in comparison to point A, and also for the wire B, the magnetic field is in the downward direction. Right? So the reference point has changed from here. If you see that the current is flowing in the plane of paper, it is like this. So you can say that the magnetic field will be in the upward direction. But if you come to point C, then this is going downward and you have changed the side. So this will also be in the downward direction. Then magnetic field, you can use Ampere's circuital law. Then this will be B dot dl. That means B into 2 pi. Now if you calculate the distance from point C to first wire, it is A by 2, and again from point C to the second wire, it is again A by 2. So the radius will be 2 pi and radius will be A by 2 is equal to mu naught. For first wire, it is 2I. So that means B1 will be having the value of mu naught I upon, this 2 cancels out, this is pi A and this will be 2. So 2 mu naught I upon pi A. And similarly, if you calculate for second wire, this B2, then this distance is again A by 2. So B dot dl, dl is again 2 pi A by 2 is equal to, here the current is I, here it is 2I, but in this case it is I. So that shows B2 is equal to, so this 2 will go here and this 2 cancels out. So this is mu naught I upon pi A. Now for both the wires, the magnetic field is in the downward direction, so we have to simply add these magnetic fields. I hope you're getting the thing, because here the direction was reversed, but here in this case the direction is same. So the resultant magnetic field on point C will be the sum of magnetic field due to wire 1 plus magnetic field due to wire 2. So this is 2 mu naught I upon pi A plus mu naught I upon pi A. So 2 plus 1 makes it 3. So this will be equal to 3 mu naught I upon pi A. And this is the resultant field at point C. This is the resultant magnetic field at point C, 3 mu naught I upon pi A. And we have calculated it very easily using the Ampere's circuital law. So go to the laws, remember the formulas, and that will help you a lot in doing your numericals. The last is magnetic field at point D. Now it is just a fraction of seconds you can solve. Yes, so if you move to point D, then at point D, the distance from first wire, if you see, is A plus A, so it is 2A. So we can write on mu naught B dot 2 pi into 2A is equal to mu naught 2I. And for point D, the distance of second wire is A, so the radius will be A. But if you look at the direction, then for this wire it is downward, but for this wire it will be in the upward direction. So the direction again reverse, and we have to subtract. So let us write down the magnetic field at point D. So we write on B1 and B2. So B1 is in the downward direction for point D, and for B2 also it is in the upward direction, because these two are in the reverse direction. So for first pi we can write on B dot dl, it is 2 pi into 2A is equal to mu naught 2I. Or you can write on B1 is equal to, because 1, 2 cancels out, so this is mu naught I upon 2 pi A. And for B2, if you calculate, then B dot dl, this is 2 pi, and here the distance is A, is equal to mu naught I or you can write down B2 is equal to mu naught I upon 2 pi a. So these two are same. So when we calculate the resultant magnetic field at point D, and this is B1 minus B2, so that is mu naught I upon 2 pi a minus mu naught I upon 2 pi a. So that comes out to be 0. So the resultant magnetic field at point D will be 0. So even if it asks you that at what point the magnetic field will be 0. So simply look at the diagram, find out the direction and use the Ampere's circuital law. It will not be 0 at A, because here you can use the law and you can see although these are in the different direction but their magnitude is different. For point C, they will add up because their direction is same, but for point D, their direction is again opposite and there is a fair chance that these will be cancelling out. So if you just look at the magnitude using the Ampere's circuit law and solve it. So the key point, so this numerical is now done. And the key point for this numerical is simply Ampere's circuital law. And this law is for a closed loop, D dot dl is equal to mu naught I. And if you remember this law, you can solve this very easily. So let us quickly move to the next numerical. So in this numerical, we are given with a semicircle for a current loop. So in this numerical, we are given with a current carrying loop. In the first case, it is a semicircle, and in the second case, it is a quarter of a circle. And we have to calculate the magnetic field. So for this numerical, you need not do any derivation, because if you are having a complete circle, then we know that you are having a current carrying loop which is in the form of a circle, and the center is given to you, and here the direction is downward into the plane of the paper. Then the magnetic field write down as mu naught Ni upon 2r. This is the derivation we have done for a circular loop, current carrying loop, using the Biot-Savart's law, and you need not do this derivation. This is the formula direct away we are using, how we got this formula. If you want to know, if you want to go to all the details, then the lecture, the reference of the lecture, the link is given below in the description box. You can quickly go to that and find out how we got this formula. So for the numerical, you need not prove this formula. You have to direct away write down this formula that for a current carrying circular loop, the magnetic field at the center of the loop is given by B is equal to mu naught Ni upon 2r. Here r is the radius of the circle, and capital N is the number of turns in the loop. So if the total wire length is small l, then you have to divide it in 2 pi r, because if you are having a wire of length l and you are going to make a circle of it, so in order to make a circle you need 2 pi r of the length. So for one circle you need 2 pi r. So if you divide its total length with the 2 pi r, you will have the number of turns. So this l upon 2 pi r will give you the number of turns. So l is the length of the wire and 2 pi r is the circumference of the circle. So now in this case we are given with a semicircle, so that means our n here represents to a single loop. In this case n is equal to single loop, and here this n becomes half. You can see for a single loop n is equal to 1 for a circle or a circular loop. So if it is a semicircle, the value of capital N will be half. So the formula remains as such. So write on the formula, replace n with n by 2. So B is equal to mu naught n by 2 I. Here small I is given, so you can use small I. If capital I is given, you may use capital I. Mu naught Ni upon 2r. So this 2 comes down. So we have the magnetic field B is equal to mu naught Ni upon 4r. So this is the formula for this semicircular loop. The magnetic field at the center is given by mu naught Ni upon 4r. So direct away we have solved this. Similarly, we can do it easily for 1 by 4 of the circle. So for a quarter of the circle, n will become n is equal to 1 by 4. So just put the value B is equal to mu naught, replace n by 4, because the loop is now reduced to, instead of 1, it is 1 by 4th of the loop, upon I is the current, then it is 2r. So this 4 comes down and you will have B is equal to mu naught Ni upon 8R. So this is the formula for a quarter of a circle. The magnetic field at the center is given by this. So we have not done any calculation, we have not done any derivation. It is just simply we have used the formula and we have replaced n with n by 2 and n by 4 and directly we get the formula. So this is the easiest way you can solve this numerical. So this numerical is now done. So first of all, go to the theory, make it clear, and then you can do numerical very easily. All the best. Let us move to the next one. So in this numerical, we are given with a solenoid. Solenoid is a hollow cylinder over which we wrap current carrying wires and they produce a magnetic field. That is what a solenoid is. So here we have shown a solenoid. This is the axis of the solenoid. And here is the center somewhere. So from the axis, this angle is theta 1 and this angle is theta 2. Okay, so the small one is theta 1 and the larger one is theta 2. So we are given with the solenoid whose length is given as 0.4 meter, whose diameter is given as 0.6 meter, and the turns are given as 1000, and current is given as 5 into 10 to the power minus 3 amperes. Then we have to calculate the magnetic field at the middle of the axis. At this point, we have to calculate the magnetic field of the solenoid and also at the end of the solenoid. So first part, we have to calculate B at middle point of the solenoid, and second is at the end point. So let us quickly move to the solution. So the formula for solenoid is B is equal to mu naught Ni. And since we have to calculate at the midpoint, then the number of turns will be half. So we will take it as half mu naught Ni. And then we have to take these angles. This angle will be theta 1 and this angle is theta 2. So we can write it down as cos theta 1 minus cos theta 2. And this is the total number of the turns. So we write it down as capital N because the total number of the turns, and small n is n upon L. Right? So this is the total number of the turns. Never write it down as small n. It was given in the question, it is symbolized as small n, but you can write down as capital N because capital N is the total number of the turns. So small n you can calculate as this 1000 upon divided with the length. So the number of turns per unit length is small n and the total number of turns is capital N. Always remember this thing. So you can easily put the value now. It is half mu naught is 4 pi into 10 to the power minus 7. And this small n is 1000 upon 0.4. And I is 5 into 10 to the power minus 3 ampere. And now it is cos theta 1 minus cos theta 2. So since this length is 0.4, so we can write it down as 0.2. And this radius is, so the diameter is 0.6, so this radius will be 0.3. So if you want to calculate the cos theta 1, then this base is given to you and this perpendicular is given to you. Then you can calculate from this side is, so here you can make a triangle here. If this angle is say theta 1, then this value is 0.2 and this value is 0.3. Then you have to calculate cos theta 1. Then cos theta 1 will be equal to 0.2 upon this hypotenuse. So this will be root of 0.2 square plus 0.3 square. So you can simplify this. And similarly, if you want to calculate cos theta 2, then for this theta 2, will be minus of 0.2 upon under root of 0.2 plus 0.3 whole square. So that's the under root of 0.13, because this is also 0.2 upon under root of 0.13. So if you do cos theta 1 minus cos theta 2, so this minus this, so these will add up. So this will be twice of 0.2 upon under root of 0.13. So now you have all the values, solve them out. So it comes out to be the pi here, so pi into 10 to the power minus 5 upon root 3. So this will be the magnetic field at the midpoint, and this field will be in Tesla. So this is our answer at the midpoint, and at the end point we can also calculate. So we'll go to the second point, that is at the end point. So if we go to the end point, then we have to join these two. So I'm drawing it once more. So this is the axis of the solenoid. So here if you take the end point, then one angle will be with the axis, first angle will be this. So this is always 90 degrees, that is a perpendicular angle. And second will be this end point. So this angle, say theta degree. So we have two angles, that is 90 degree. This will be our theta 1, and so we have theta 1 degree and theta 2 is equal to 90 degree. So this cos theta 2 cos 90 is equal to 0. So cos theta 2 will become 0, and we'll have only cos theta 1. So we'll have B is equal to half mu naught I. N is the number of turns, so we'll multiply it with N also. So half mu naught Ni and cos theta 1, because cos theta 2 is 0 degree already. Because cos theta 2 is 0 already, plus cos 90 is 0. So this is cos theta 1. So just put all the values. B is equal to half mu naught is 4 pi into 10 to the power minus 7, and N is the number of turns, that is 1000 divided by 0.4, the value of small n. Then the value of I is 5 into 10 to the minus 3. And then this cos theta 1 we have to calculate. So again you have to make a triangle like this. Because this angle is always, you can draw here. So this angle will be 90 degree, and this is our, say, theta 1. So this distance will be the length. So this length is already given to us as 0.4 meter. And this is radius, so this is 0.3. So if you calculate cos theta 1, that comes out to be 0.4 upon, that is the base, and this will be under root of 0.3 square plus 0.4 square. So if you solve it, it comes out to be 0.8. So this is 0.8. So this Tesla will be the magnetic field at the ends. So this numerical is now done. So we calculate the values and match the answer, and this numerical is now done, and comment me in the inbox. Now let's move to the next one. So here we are given with 4 wires. This is 1, 2, these are current carrying wires, and these are slightly tilted. So this is carrying the current I1. I'm drawing the diagram as such given in the question. This is I1 upward, then I2 current flowing in the downward direction in the plane of the paper. Then I3 is upward in the plane of paper, and similarly I4 is upward in the plane of the paper. So these are the 4 current carrying wires. And then we have 3 loops. First loop is L1 around these two, and second loop is L2 around these 3 wires. So this is L2 like this, and it is also like this. And the third loop is continue down like this. The third loop is somewhere here between this I2 and I3 current carrying wire. So this is L3. Right? So we have to find out the value of B dot dl, that is Ampere's circuit law. If you make a closed loop around a symmetrical surface, then you can use Ampere's circuit law. Then you have to find out this B dot dl for the loop L1, L2 and L3. Right? So simply, if you want to go to the solution, we have to use Ampere's circuit law. So let us go to the solution. Ampere's circuit law is coming of great importance. Yes. So we can write down the general formula for Ampere's circuit law. B dot dl is equal to mu naught I. That is the general formula. We will be using Ampere's circuit law formula that we'll be utilizing to solve this numerical. So let us go one by one. Let us first move to loop L1. So for loop L1, you can simply write down B dot dl. B is a magnetic field and dl is a closed loop. You can take a cross integration of this, so that will calculate the total area is equal to mu naught. Then come to the loop 1. Then this is our loop 1 L1. It is between 2 wires. So these are flowing in the opposite direction. So we have to take I1 minus I2, since the direction of current in these 2 wires which are bounded by the loop L1 are in the different direction. So we have to take, we have taken I1 as positive and I2 as negative, because if you see the magnetic field lines according to the right hand rule, then for the I1 current it is anti-clockwise and for I2 it is clockwise if you see from the top. So you can write it on B dot dl is equal to mu naught I1 minus I2. That simple it is. Now come to for loop L2. Then again you have to write down Ampere's circuit law. B dot dl is equal to mu naught. Now this loop L2 is binding I1, I2 and I4. So if you use the right hand law and if you show the direction of flow of the current, then your I1 is in the anti-clockwise direction if you see from the upward direction. So this will again be I1, then this will be in the clockwise direction minus I2 and I4 is again in the anti-clockwise direction. So this is with a positive sign. And just remember all these directions we are seeing from the above. So this will be clockwise, I2 will be clockwise, I1 is anti-clockwise and I4 is anti-clockwise. So similarly we have written very easily for loop L1 and for loop L2, and if you come to loop L3, then again B dot dl is equal to mu naught. Now it is not binding any of the current. So the value of current here is 0. So this B dot dl comes out to be 0 for loop L3. So that easy it is, but do not get confused. Either you get it as a subjective question or it is an objective question. So options are given to you, then you have to pick out the right options. You have to do either I2 minus I1 or I1 minus I2. So look from the upward direction, then you will see that again use the right hand rule, that if you fold your fingers in the direction of magnetic field lines, then your thumb will point out in the direction of flow of current. So similarly you can find out that for I1, if you see from the upward, then these are the anti-clockwise direction. For I2 it is in the clockwise, for I3 again it is in the anti-clockwise, and for I4 it is in the anti-clockwise direction. So that way you can write down the positive and negative sign corresponding to all these currents very easily. Right? So do it right. Don't forget the direction. Don't forget the formula. And be alert. Yes, let us move to the next one. My dear students, do it right always. Next one. So in the next one, what we are given is that we are given with a semicircular loop, and it has a center C. The current which is flowing in the anti-clockwise direction is capital I. So these two ends of the semicircles are given as P and Q, and the radius of this semicircular structure is given by capital R. So R is the radius, C is the center. So as you can see that the current is flowing in the anti-clockwise direction. So the magnetic field will be downward. As you can see from the right hand rule, your magnetic field will be downward. Just hold your finger in the direction of your current and then get the magnetic field in the downward direction. So we have to find out the resultant magnetic force, FB magnetic force, and torque, tau, at point C and point B. C is the center and P is one end of the semicircle. So we'll go one by one and we'll find out first the magnetic force, and then we have to find out the torque. So let us quickly go to the solution. So the formula force is F is equal to ILB. We have to use whenever there is a magnetic field. So the current flowing is I, so we can write it down. So this is the formula we will be using. Simple, just write on the formula. So the current is I. The length of the wire, if you see, then this will be twice of R. And the magnetic field is P. So I to RB, that is the magnetic field on the center. If you can see, this is, so this can be written as equal to a current carrying straight wire PQ, whose distance is 2R. So this is I, the length is 2R, and the magnetic field is B. So you get it as I to RB. And if you calculate the direction of the force, you know the direction of the current, you know the direction of the magnetic field. Then if you calculate the direction using the right hand rule, then it is radially outward for the point P. It is radially outward here, and again for the point Q it is radially outward. So the torque in this case will be 0. This force you can calculate using the right hand rule, that is, your thumb will point in the direction of the force and your index fingers will be in the direction of magnetic field, and your middle finger points out in the direction of current. So if you do it like this, put your right hand like this, then you will get that the torque, the force which is acting here on point P and Q is radially outward. So both the forces are in the outward direction, so there is no resultant torque. So torque is 0 for the center C. And for if you come to point P, if you want to calculate, it is I L cross B. Then I is the current which is flowing. L you can write down as R d theta, because if you take an arc and the angle which is, if you take this point P and this angle will be theta and this radius is R, so this length will become, because the formula is angle is equal to arc upon radius. So this length L will be equal to R d theta. So we have written L as R d theta, and this is B, and the distance, if this is the L, the length, and this B is downward, so the angle between these two are, because these two are mutually perpendicular, so the angle between these two is 90 degrees. So B sine 90 degrees. So this is the force that is acting, magnetic force at point. These are the two results for point C, and this is the result for point P. Now we have to calculate the torque. Torque is equal to R cross F. So that is equal to, just put the value of F. This is I R d theta, B sine 90 degree, I L cross B. And this R, if you see, then it will be R sine theta. And we have to integrate it for 0 to 5. Then the resultant you will get is 2IdR squared. So that is the torque that will be acting at the endpoint. So this numerical is now done. Simply you have to use the formula F is equal to IL cross B and tau is equal to R cross F. And then simply do the mathematics and you will get the answer. Here we are given with a loop of this kind. And the current is flowing like in this direction. The current is given as capital I. And here there is a center C for the semicircular loop and the radius is given as capital R. Right? Then we have to find the magnetic field B at center C. We are given with one more structure that is like this. And here the current is flowing I in this direction. So for these two consequent loop it is in the opposite direction, and here's the center C somewhere. And this inner semicircle is having the radius A and the outer semicircle is having the radius B. Then again we have to calculate the magnetic field B at center C. So these are the two cases where we have to calculate the magnetic field at center C. And again we have to use Ampere's circular law. So let us quickly move to the solution. So if you come to this loop, then write down the Ampere's circular law. B dot dl is equal to mu naught I. Then this is B into 2 pi r for a complete circle. And here it is a half of this. So this will be 2 pi r upon 2. That means pi r is equal to mu naught I. So again we have to use the derivation we have already done for a magnetic field due to current carrying loop. That is equal to B is equal to mu naught I upon 2ar. Mu naught I upon 2r. Always remember this relation for a complete circle current carrying circular loop, and a magnetic field at the center is always mu naught I upon 2r. We have done up with this derivation. Just quickly, if you want to move to the lecture, go to the link given below and go to all the theory we have done, and this is the final result to be remembered, mu naught I upon 2r. Now this is just a semicircle, so you have to just put it half. This is for a complete circle. That is a formula for a current carrying complete circular loop. So now we are given with a semicircle, so we'll just do it half. So this is half of a full circle, mu naught I upon 2r. So direct away you will get the formula B is equal to mu naught I upon 4r. So that is the correct answer, correct option. And this is done very easily if you remember this formula. So the first part we have done for this loop. Now second we have to move on with this loop. So here we can see there are two semicircular loops. So if this is our second part, we'll try to solve it here. We will do individually for each of the loop. First inner loop with radius small a and the outer loop with radius small b. So we can write it down as that the magnetic field for the inner loop will be mu naught I upon 2a had it been a complete circle, but it is a semicircle, so put it half. Similarly, B2 magnetic field due to a complete circle of radius b small b is this, but again the outer circle is a semicircle, so just do it half. Now here you can see that the current is in the different direction, in the opposite direction, so you have to just subtract them because the direction of magnetic field will be opposite. If you want to know the direction, then for the inner loop it will be downward, and for the outer loop it will be in the upward direction. So these are in the opposite direction. So simply calculate the resultant magnetic field. B is equal to B1 minus B2. So this will be equal to mu naught I upon 4a minus mu naught I upon 4b. So if you can take mu naught I upon 4 as common, then you are left with simply 1 upon a minus 1 upon b. So that is the correct option. So always use the formula. If for a semicircle, do it half. For a quarter of a circle, do it 1 by 4. And whenever you are given with a combination, then always remember the direction of the magnetic field, and accordingly they will add up if they are in the same direction, and you have to take a difference if they are in the different direction. So that is the tip for this numerical, and this numerical is now done. Now let us move to the other one. That is very simple a question, but we'll do one of this type so it will also clear to you. We are given with a charged particle which is moving. And if there is a charged particle which is moving, that means it's carrying a current, and whenever there is a current, there is a magnetic field. So if you have such kind of numerical, always come to the point that this is a numerical from the magnetism due to moving charges. So this is a charge which is moving, and the acceleration for this charge is given to you as, acceleration is a vector quantity, so it is given to you as in form of unit vectors 2i cap plus xj cap, that is acceleration of a charged particle, and it is moving in the magnetic field which is given as minus 3i cap plus 2j cap minus 4k cap. Then we have to find out this value of unknown quantity x. So let us move to the solution. We know that the formula for force is given as F is equal to IL cross B. So this force is perpendicular to the direction of the current as well as to the direction of magnetic field. So here this acceleration is always related to the force, because whenever there is a force there is an acceleration. So this force we can relate to the acceleration, and the direction of this force is perpendicular to the current I and the magnetic field B. So since F is perpendicular to B from this formula, then the acceleration A will also be perpendicular to the magnetic field B. That means the angle between A and B is 90 degree. And we know that cos 90 degrees is 0. And cos theta comes in dot product. So if you take a dot product between the two vector quantities, acceleration and magnetic field, then it will be 0. So the dot product A and B will be 0. This is a simple physics you have to apply to solve this numerical. Now you have the value of A, you have the value of B, then take the dot product. Put the value of A as 2i cap plus xj cap, then take a dot product because this cos 90 is 0 and theta is 90 degree, and this dot always stands for cos theta. So then write down the value of B, minus 3i cap plus 2j cap minus 4k cap. Now take a dot product. Then this will be I dot I is 1, then this is minus 6, then x multiplied with 2, then this is 2x, and there is no k, so 0 into k is 0, so this will be equal to 0. Now it is very simple, 2x is equal to 6 or x equals to 3. So the acceleration of the particle is 2i cap plus 3j cap is the answer. So this numerical is now done, and what we have utilized here is the formula of magnetic field F is equal to IL cross B, and from the formula itself you can see that if there is a cross product, then current is perpendicular to the force as well as magnetic field is perpendicular to the force. So using these two logic you can solve this numerical very easily. So that's all for today. If you like this lecture, if you like the way we solve the numericals, you want to have some queries, you want to comment, then please like and share and comment in the comment section, and go to the lectures and subscribe to our channel Physics Class so that you can continuously receive notifications for more such lectures and more such solve numerical problems. Thank you.